Hello students, so continuing our lectures on electronic devices, we'll first start with calculate the charge concentration. That is Ni in an intrinsic semiconductor. And we assume that the band gap is much higher than kT. So at room temperature, it has been given that the value of intrinsic carrier concentration, that is in power 10 per centimeter cube. We need to find the value of Ni at 500 Kelvin. So the expression of intrinsic carrier concentration Ni is equal to 2 to the C and V into e to the power minus Eg by kT. We assume these two quantities to be constant. There is no change in these two quantities. So therefore, Ni at 300 Kelvin divided by Ni at 500 Kelvin, if we divide these two, full expression that remains is e to the power minus Eg by energy corresponding to 300 Kelvin, that is 0.025 electron volts, minus e to the power minus Eg by energy corresponding to 500 Kelvin, that is it's not 500, it's actually 450. So that is e to the power 0.038 Kelvin. So this gives us expression, and the value of Eg for silicon is 1.1 electron volts. Oh, sorry, it's 2 kT. So this will give you the corresponding value of the intrinsic carrier concentration at a higher temperature. Now, there is another term called the electron affinity. This is the energy between the conduction band minimum. So we have the conduction band, the valence band, and this is the band gap Eg. This is the conduction band minimum EC, and this is EV. and this is the vacuum. So the energy difference between the conduction band minimum and the vacuum level is the electron affinity. So if we have an intrinsic semiconductor, with band gap say equal to 3.4 electron volts, which corresponds to 364 nanometers, since E is equal to hc by lambda. So if this is the case, then the energy required for absorption should be higher than this value. So for absorption, H mu should be greater than Eg, and so in terms of wavelength, lambda should be less than 364. So any wavelength which is less than 364 nanometers will get absorbed. Now if we assume that the number of concentration in the conduction band is equal to the number of carrier concentration in the valence band, then if we increase the temperature from room temperature to 1600 K, then what can we say about the position of the Fermi level? So now, according to the Fermi-Dirac statistics, at absolute zero, the Fermi level follows a step function. However, when the temperature is little more than zero, it follows a not a step function, but it crosses through this point. So what we can say is that the Fermi level will be exactly at half of the band gap if the temperature is more than absolute zero. Now what will happen when we have what happens to the Fermi level based upon the ratio of the electron and hole mass? So the Fermi level can be expressed as the valence band maxima plus half of the band gap minus 1 by 2 kT Nc by Nv. This is one expression. And in terms of the mass of effective mass of hole and electron, we can write EFI as equal to EV plus Eg by 2 minus 3 by 4 ln ME star by MH star. Next is if somebody tells you to find out arrange the following semiconductors in order of increasing carrier concentration. And we'll assume that all the semiconductors are ideal and are at room temperature. Now, intrinsic carrier concentration. We use the following semiconductors. They are gallium arsenide, there is silicon, and there is germanium. Intrinsic carrier concentration in terms of centimeter per cube turns out to be, for the case of gallium arsenide, turns out to be 2.4 into 10 to the power 6. For the case of silicon, it's 10 to the power 10. And for the case of gallium arsenide, it's 2.3 into 10 to the power 13. So germanium is having the highest carrier concentration, so we can easily arrange the carrier concentration of the following materials or the following semiconductors. And gallium arsenide having the least one, followed by silicon, followed by germanium. Now we know that the expression of intrinsic carrier concentration is equal to NCNV e to the power minus EG by 2 kT. So if we plot log of intrinsic carrier concentration versus 1 by T, what we can have, let's write it once again. Ni is equal to NCNV e to the power minus EG by 2 kT. Taking the log of Ni will give you log of NCNV minus EG by 2 kT. So if we would like to plot ln Ni versus 1 by T, so this with respect to this, so using y is equal to mx plus c. So this happens to be the c part, the constant part, and the y part, and this is the 1 by x part, 1 by t. So m, which is the slope, is equal to the band gap Eg.